Last time we discussed the inverse Z transform. Today we are going to continue our discussion with inverse Z transform. We are going to discuss the second method called power series expansion. We mentioned the theory behind this last time, and today we are going to use an example to show how to do this. Right? Suppose example is given like this: the Z transform equals log 1 plus a times z to the negative 1, and the region of convergence is z is greater than a, so outside of the circle. And how to do this? If you look at the table, right, the common pairs, we don't have anything looks similar to this. So that means we cannot use that method to do this. Right? Instead, we are going to use the power series expansion. If you still recall in math that we can represent a signal, a function, with a power series is Taylor expansion. And we are going to use this method here. Right? Recall that if x is less than 1, then log 1 plus x can be written as the sum of from 1 to infinity, negative 1 to the n plus negative 1 to the power n plus 1, and xn over n factor over n. Right? That is a math Taylor expansion. So we are going to use this one. Look at here. 1 plus x, okay, that is x. We can assume this one is x. Then we just get xz equals log 1 plus x. So that will be equal to n equals 1 to infinity. And here, negative 1 to the n plus 1, and n here, we just copy all this constant. And this x will be replaced by a z to the negative 1. Right? So that one will be a z to the negative 1. This is x, then to the n. And we are going to rewrite this as n equals 1 to infinity, and negative 1 to the n plus 1, and n, and this one will be a to the n, and z to the negative n. Right? So we just use a Taylor expansion in math, and then we write the given Laplace Z transform into this power series. Okay, so now we look at this. Can you tell what is the time domain signal xn? Look at this. Recall the definition of the Z transform. The definition of the Z transform is xz equal to the sum xn times z to the negative n. Okay, so here z to the negative n. That means that this part here will be the xn. Does that make sense? So we compare these two, the definition and our problem, then we can easily write out the time domain signal. So let's see what is the leftmost non-zero value. What's the leftmost value? Because this starts from 1, so that means we do not have any when n equals to 0. So that means x0 equals what? Equals nothing, right? We don't have this. So equals 0. And before that, we don't have anything. Right? Then x1 equals what? x1 means this is 1. This one is negative 1 here. This is 8, and so this is negative 1. So that means this part is x1. So x1 is 1. This one is 2. So this is 1. So this is equals a, right? Yeah? When n equals 1. So this is 1. What is x2? x2 means when n equals 2. Because this is x z to negative 2. N equals 2, so on the top that will be a negative 1. On the bottom that will be 2. Right? So this negative half, and this one will be a squared.
So when x is 1 and it equals to a, wouldn't z to the negative n, wouldn't that be a negative?
This one is this part. It's definition here. This is the same as this one. We are looking for xn. Right? In the definition, xz equals something, the time domain signal multiplied by z to the n, and negative n. So this is z to the negative n. So you just compare these two. So this one is the signal. Right? And we start from 1, 2, 3, 4. So 0 and before, so less than or equal to 0, we don't have anything. And the first one is 1 equals a, 2 equals a, and 3, and so on. So we can get this. Right? We summarize this, and we can write as xn. We do not want to write all of them one by one. So this sum is equals negative 1 to the n plus 1, just this one here, over n, and a to the n. So that is it. But we are going to start from n equal to 1. Because before that, we don't have anything. So what I write is u n minus 1. So that means start from 1. Any question on this?
So this is, you did normal, oh, never mind.
What we do here is, if I give you a z transform, right? If you can recall any mathematic formulas that can break this one into a power series, right? For this one, luckily we memorized that log 1 over 1 plus x equals this one. And we have some other identities like Taylor expansion, like cosine something or sin something there. Again, in the math, they give you a table. So you need to refer to that. And we bring this, then we compare our z transform with the definition. So we can easily determine the time domain value. Okay, any question on this? It's good? Wait, okay. Good? Right? This is a power series expansion. The next one will be what's this? Partial fraction expansion. Right? We know this very well in inverse Laplace transform. But there's a little difference here, so we still need to review this. Suppose we have xz is given in this form, b0 plus b1 z to the negative 1 plus b2 z to the negative 2 plus all the way to b capital M z to the negative m on the top. On the bottom, we have a0 plus a1 and z to negative 1 plus a2 z to the negative 2 plus all the way to a capital N z to the negative n, like this. Polynomial on the top, polynomial on the bottom. What we do is we are going to, if we recall in inverse Laplace transform, we first need to determine the degree on the top and the degree on the bottom. So if necessary, we need to use a long division, right, to make sure this xz is rational. So that still works here. So we are going to bring some terms that are equal to 0, m minus n, z to the negative dr, and z to the negative r. So this part is the long division part. You use this one if necessary. Use this one, divide by this, you get several terms. Long division. Again, you recall what we did in Laplace transform. We do this long division first. Once the degree on the top is lower than the bottom, then we can use the partial fraction expansion. So that will be equals some terms here. So this one will be equals the sum, because we are going to have several terms. So n, k equals 1, and k cannot equals I, equals ak 1 minus dk z to the negative k. So those are the, you just write it like this. Here, later time we are going to use the example to show how to do this.
Is that ki?
K not equal to I, k not equal to I. And this part will be like the unique root for this one. Then we are going to have some repeated root. So this one will be m equals 1 to s and cm and 1 minus dj di and z to the negative 1 and to the power of m. So this one cannot be equal to I because I is here. I is a repeated root, and with the multiplicity equals m.
What is that you got on top of that?
This one?
No.
This one?
Yes.
S. We are going to have S, this kind of terms. So m is the S is the multiplicity of this root. Again, we use the example better to show this. But this one is the formula, is the general formula. We know how to get this BR, right? By long division. Then for this unique root, we are going to use remember the partial fraction expansion. That's easy to do it. But this part we need to start from the highest order and go back to the lowest order. So what is AK? The BK is easy to find. So what is AK? AK equals 1 minus dk times z to the negative k. This one times xz. We use this part multiplied by this xz. Then let z equals dk. This one is very similar to in the inverse Laplace transform, right? Equals x s times the bottom, then let the s equals the pole, right? So that's the same thing here. And for ck, right, cm is more complicated. We already know that from inverse Laplace transform. So I copy the formulas here: s minus m and factorial. Negative di and s minus m 1 and all this d differentiation and dz to the negative 1 s minus m and 1 minus di z to the negative 1 and s then times xz here like this. Again, the formula is tedious, but we don't need to memorize this. We know how to do this in a Laplace transform already. Those are unique roots. These are repeated roots. And all these coefficients can be complex. Here, if we look at this clearly, we use z to the negative 1 instead of z. Some other reference book, they may use z, but in our textbook or in our lecture notes, we use z to the negative 1. we treat z to the negative 1 as one variable. Okay. We are going to have examples to show this. Can I erase everything? This one is in the slide. Right. Example 1 is 1 is 2. xz equals 1 minus a quarter z to the negative 1 and 1 minus half z to the negative 1, and the region of convergence is z is greater than half. Right, so how to find the inverse z transform for this one? This is rational, so we need to use a partial fraction expansion, and we treat this one as one variable. Right? So what we do, look at this one. What is the root for this one? That means the pole. That means we make the bottom part equal to 0. So for this one, z will be equal to a quarter. If z equals a quarter, z inverse equals 4. Okay? 4 times a quarter equals 1. 1 minus 1 equals 0. So that means this is a pole. So again, easy to do this. This coefficient here, negative this coefficient will be the pole. So what is the pole here? Half, right? So this pole here equals 1/2. Because when z equals 1/2, z negative 1 equals 2. So 2 times the negative half equals 1. So 1 equals negative 1. So 1 plus negative 1 equals 0. So again, this one will be the pole. So we can see we have 2 poles. One is a quarter, one is a half. They are different. They are unique. Right? So that will be the second part in the formula. Right? We don't have the first part. Why? Because this one is already rational. The degree on the top equals 0. The degree on the bottom is 2. We are talking about z to the negative 1. So the degree on the bottom equals this negative 1, so multiply together equals 2. So the degree on the bottom equals 2. The degree on the top equals 0. So that means this is already appropriate. So we don't need the long division. So that's why the first part, BR times z to the negative part, we don't have that part. Right? We only have this one. So this will be equals, and we do not have a repeated root. That's the next part. All this Cm something, we don't have that. So this question is very, very simple. Does that make sense to everybody? Right, now let's do this. So this one, we are going to bring this into 1 minus a quarter z to the negative 1, and a on the top. And there's another term, 1 minus half z to the negative 2, b on top. This is good? Inverse Laplace transform. We record that, then we're going to get. Okay, so now we determine what is A. A equals, from the formula here, or what we record in the Laplace, inverse Laplace transform, is xz times this part, right? Because we are looking for A, so times 1 minus here, this, then let z equals what is the pole?
Z equals 1/4.
1/4, right? Let z equals a quarter. We need to be able to determine why z need to be equal to 1/4. That is from here. Right? So now what is this? xz is this one, is here. Right? We multiply by this part, which is this, which is this. So that means this part is gone. Right? So we have only 1 over 1 minus a quarter, half z to the negative 1. And we let z equals a quarter. Right? Then you plug this one into here, so this one equals 2. The next one is to determine b. B equals what? xz times 1 minus a quarter, half z to negative 1, right? Multiplied by this, right? Then let z equals half, right? Equals the pole here. Then that one will be equal to xz again here, multiplied by this part, so this one is gone, cancel. So we have 1 over 1 minus a quarter z to the negative 1, and we let z equals half. Right? We plug this one into here, and that result, oh, sorry, this one equals negative 1.
Yeah, that's not right.
Okay, so this one equals negative 1. Right? My mistake. And this one equals 2. I copied the wrong line. Okay, so is everything good so far? Right. In the homework or in the test, what you do is you need to copy xz equals, just plug this one into here, this into here. But for me, in the board, I will just remove this one, everything, I just change this one to here. Does that make sense? So you know what you should do, okay? So this one equals negative 1, this one equals 2, I will remove all this 2. Okay? You don't do that, right? What you do is you copy this one under A and B. Show me how you calculate A and B. Is everything good here? Okay, next one, we calculate the Z transform, inverse Z transform. So that is easy. We use the linear property. The inverse Z transform for this one is the inverse Z transform for this plus the inverse Z for this. Okay? And what is this one? Keep in mind, the region of convergence is outside of the circle. So that means the signal is a right-sided signal. Now, anyone still remember the common pairs of Z transform? What is this? 1 minus a z to negative 1. So it looks like this is exponential, right? So that one must be a to the n un. So that one will be a quarter. This is a, right? And n and un, and there's negative in the front. Yes? Alright, that's the first term. What's the second term? The second term is also a right-sided signal. So it's also in the form of something times un. And this is also a exponential. What is a here? Half, right? Okay, so that is a half n and un here. And we have a 2 in the front. Right? We can combine these two, so that will be 2 to the half, half to the n plus 1 minus this to the n, then together times un, and make this compact. Minus 1. Or we can just like it, there's 2 here. Right? If you want to combine this and this one is supposed to be a minus 1. Right? A minus 1, not plus 1. But maybe you can just do like this. Question on that? This is good, right? We know the procedure how to do this. The most important part is to determine A, coefficient A and B. Okay, we calculate another one.
Don't do it, don't do it.
Right, I write here. Right, we still have space. Example 3, so xz equals 1 minus 2z to the negative 1 plus 4z to the negative 2. And over 1 minus z to the negative 1 and 1 plus 2 z to the negative 1. The radius of convergence is again a solid circle, so it's right-sided signal. How to do this? Can we just do like that? Okay, we need to do the long division. Why? Because the degree on the top equals 2 or negative 2. 2, right? Because we are talking about z to the negative 1. So this one equals z to the negative 1 to the 2. So this is the degree. The degree equals 2, right? Not negative 2. So the degree on the top equals 2. What's the degree on the bottom? Also 2. So they are the same. That means this is improper. Right? So we need to do the long division first. The long division first is we are going to, so here is the key. So I use 4 negative 2 minus 2z plus 1. I need to use it this way. And divided by this times this. So that is negative 2 z to the negative 2. Everybody see this? That is this term times this term, right? Then this term times this term times this, so that is plus z to the negative 1. And then plus 1. Okay? Good? You need to persuade yourself, right? So you do this by yourself and you see, okay, yeah, that is correct. Because later time you're going to do by yourself. Then this one divided this, we only consider the first term here. So 4 divided by negative 2 equals negative 2, right? Negative 2 we'll put in here. And so this one is 4 z to the negative 2 plus 4 z to the this one is negative 2 z to the negative 1, then minus 2. Right? And we subtract, that one will be 3 only. Yeah? Alright, now let's write. So that means xz equals negative 2, that is the quotient, then plus, and the remainder is on the top. We still need to copy this one here, 1 plus 2 on the bottom. Okay, what's next? Partial fraction expansion applied to second term, right? This term is the first term in the formula, BR or something. So this is already here, so we don't care. Right? So we just copy this, then plus, what's the pole on the bottom? This one equals 1, this one equals negative 2. So they are different. Right? So now things are easy. So this one here is A, 1 minus z to the negative 1 plus 1 plus 2z to the negative 1, and that's B. Then we are going to forget this 2, negative 2 part, only focus on this one here. Right? That question is very similar to that one. So we can calculate A and B, right? So I won't bother you here, but you calculate A and B by yourself. The result will be A equals 1, A equals 1, B equals 2. This is good? Alright, now what is the inverse Z transform? The region of convergence is outside the circle, so it is the right side of the signal. Alright, let's do this. What's the first term? Now we can consider the table. What is the negative 2? Is this negative 2 delta n? Because delta n gives us 1. So there's negative 2 coefficient before that, right? And this one plus, right, look at that. This is un, right? Is this un?
Yeah.
Okay, this is un. This one, what is A? 2 or negative 2? Negative 2, right? Look at all here. Minus half, A is half. Minus quarter, A is quarter. So plus 2, that means A equals negative 2. So negative 2 to the n and un, and there's 2 here. So we have 2 here. Okay, that's it. Can you do all these questions by yourself? No? Why is that no? Which part you cannot?
Just need to pray.
You need to practice, right? So now you can recall. The first step one is you determine if it is rational or not. If no, that means you need to use the long division to reduce the degree on the top. If yes, then you just use the partial fraction expansion, determine the coefficient A and B. Luckily, so far, all those roots are unique, so you don't need to do anything else. Right? You just use the method to determine coefficient A and B. So next one is example 4. Xz equals 1 plus a squared z to the negative 2. And the region of convergence is again outside the circle. For this one, looks like we are going to again to determine the root, and we are going to factorize the denominator. So 1 plus a squared z to negative 2 equal to 0. So this is 1 plus az negative 1. 1 minus az to negative 1. Is this correct? Is 1 plus x times 1 minus x equals 1 plus x squared. Is this correct? No. Okay, this 1 plus x, 1 minus x equals 1 minus x squared, not equals 1 plus x. So this one is not true, right? Because this plus something, 1 minus something equals 1 minus a squared. This one, not plus. Right? So actually, it must be the j before that. There's j before that. Right? So we are dealing with complex numbers. Right, so now we know that. So I'm going to write. So this one will be equal to 1 plus j az times 1 minus j a z to negative 1 here, and on the top of this. Are these two roots unique? This one is negative ja, this one is a positive ja, so they are different. So yes, they are unique. So we can still use the method discussed because they are unique roots, so we can still use that method. Right? The only difference is we are dealing with complex numbers here, but that is not a big deal. Right? So this one will be equal to 1 plus j a z to the negative 1 constant a plus 1 minus j a z to the negative 1 constant b on the top. We use the same method to determine a and b. Right? And the result will be equals a equals half. Right? So a equals half. And b equals half too. Right? Also equals half. So everybody knows how to do this, right? The only difference of this is we need to deal with the complex numbers. That's all. Okay? Now, what is xn? Is this exponential? Because the region of convergence is outside of the circle, so this one will be half. Anyone can tell me what's half what? A to the n. What is a? Negative ja. Yeah? Right? To the n times un. But I will going to put the un together here. Okay, then plus another half. Okay, so I will put this together. And this one will be ja to the n here. And then un. So that is the result.
What are your poles?
Huh?
What are your poles?
The pole is negative ja.
Okay. So how did you plug in ja and get a half?
Half is here. This is half.
Alright.
This is a to the n times un. This half again is here. And this a equal, in the formula, this a equals negative ja, is a positive ja, so ja to the n, then times un. Then looks like this is good, but we can still further simplify this. And the result, if further do this, it is an times cosine pi times n over 2. Use Euler's identity. Use Euler's identity, we can further simplify this one. Can you draw this figure?
Here.
This one is in the first midterm, right? Still remember that? Let you draw this thing, the cosine pi n over n. So when n equals 0, this one equals 1. When n equals 1, that one equals 0.
That's an n?
And this is pi n over 2.
Okay. 2.
Okay, any question on this? Okay, what are we going to do next? What kind of example I'm going to give you? With a repeated root, right? Right, so we need to discuss that. Right, this is example 5. Xn equals 7 minus 5 z to the negative 1 plus z to the negative 2 over 1 minus half z to the negative 1 to the cube. What is step 1? determine if this is appropriate. Yes or no? No? What's the degree on the top? 2. What's the degree on the bottom?
3, it's fine.
3. So that is appropriate, right? So we don't need to do the long division. But the difference between this and what we discussed before is this one looks at the root equals half is repeated with a multiplicity of 3. So what do we need to do based on our memory from inverse Laplace transform? Anyone can tell? How many terms do we have here? 3 terms. Right? The first term is A on the top. What is here? This? Okay. Then what's the second term? 1 minus half z to the negative 1. What's the second? Square, right? And then the next one will be C, 1 minus half z to the negative 1 cubed. Right? We cannot have only this term. We need to have this term and this term. Right? That is. Which one we should find out first? A, B, or C? Which one to start? C. Okay, good. We start from the highest order, right? So C equals, how to find C? Right? We have formulas given in this one, but I don't suggest you to memorize, right? So we just use the what we learned in inverse Laplace transform. So this one will be xz. The highest order is easy, right? We just multiply this. So multiply by half z to the negative 3. And let z equals what? 1/2. So what is this? Right? I will do this first. This one will be equal 7 minus 5z to the negative 1 plus z to the negative 2. So this, right? xz times this is this one. Because the bottom is cancelled. We only have the top. Yeah? Right. Then z equals 1/2. So what is this? So what is on the what is this? Z equals 1/2. So that means z inverse equals 2. So this one is 7 minus this is 2, so minus 10, and plus this is 2 plus 2.
Why did you do it?
Oh, this one is a quarter, so plus 4, right?
So why did you? I thought we'd done that solve for C as far as, and then you just do B and A. Why are you continuing?
We start from a C, right? C equals this thing multiplied by this,
Yes.
and let z equals 1/2,
Yes.
right? This thing multiplied by this, the bottom is gone.
So we can just stop right there.
Yeah.
Leave
So
it.
excuse me. C is so 7 minus 5z to negative 1 plus z to negative 2.
When z equals 1/2.
Yeah.
So z equals 1/2 means z to the negative 1 equals 2.
Aren't you done there? In that A?
What do you mean A?
Or excuse me, in that C? Like, in
Yeah,
that
we need to evaluate what this value is here. That's what we are doing.
All right.
Right?
Continue on then, I guess.
So what you get? You said this is done? We need to plug this z here into this one to get a number. What was your question?
I guess I just don't understand. I mean, as far as I know,
This part is this times this.
Yeah.
Then we need to evaluate z equals half.
Yeah.
So we make z inside here equals half. We get a number here. That make sense? That's what we are doing, right?
Yeah.
Okay, so z equals half means z to the negative 1 equals 2. So that is 7 minus 10. And z squared equals a quarter, then negative equals 4, so that is this. So this one equals what? What is this? You are not following this, right? Still here?
-1.
Negative 1 or positive 1?
Positive.
Positive 1, right? 7 minus 10 plus 4. Everybody is good? You need to do this by yourself. Is this good? Okay, so that's nothing, right? We already done this several times. Now the next part is different, right? So what's the next one? B, right? We calculate B. How to do B? B is differentiation with respect to negative z to the negative 1. In inverse Laplace transform, this one is to the ds. But this one here is, what's this part? This part is xz times this. So which is this one? In the formula you can see that is the differentiation with respect to z to negative 1 of this part, which is this one.
So why are we taking the derivative?
Because we are going to do this one. That's the first order differentiation. Then this one we need to do the second order differentiation.
And that's because we have a cube root.
Because this is 2 here, this is 1 here. Right? But we start from 3, we don't need to do the differentiation. Right? So here is 7 minus 5z to the negative 1, then plus z to the negative 2 here. And after we evaluate the differentiation, we need to make z equals make z equals what? Half again, right? Same thing, because the half is the root, right? Now that you need to pay attention here. This differentiation is with respect to z to the negative 1, not to the z. For safety, you may want to rewrite this one as 7 minus 5x plus x squared. You want to replace x equals z to the negative 1. Replace this. So this one is here. Then it's d dx. You may like this form, but they are the same thing. Does it make sense? Okay, so now you write z to the negative 1, just represent it with x. So this is 7 minus 5x plus x squared, then d dx. You can do this, right? What's this? What is this?
2x minus 5.
This is 2x minus 5. Right? I will go this way. Okay, same thing. Right? So negative 5, then plus 2x. Yes? But the x equals z to the negative 1. Right? So that is the differentiation. And then let z equals half. So what is this? And if you recall the formula here, there are some coefficient before that. And there is a negative 2 here on the front. Remember we recall all this Cm here. There's some coefficient here on the front. So that one is negative 2. So that's negative 2 here, and this. And so what is this? This one equals this one equals 4, right? Plus minus 5 equals negative 1. Then times this, negative 1 times negative 2 equals 2. It's good?
Where do you get the negative 2 from?
Negative 2 is given in the formula. So in the last, the CM, remember at the very beginning, said we break this one is long division part and unique root part and the repeated part. There's some coefficient before that. Right? So that is the coefficient.
I'll take your word for it.
Okay, the question here. All right, now the next one is next one is to find A. A will be equal to, we have a coefficient also, and if you plug into the root and that number, this coefficient equals 2. It will be d squared dz negative 1, second order differentiation, with respect to 5z negative 1 plus z to the negative 2, this. And again, we let z equals half. We need to take the second order differentiation of this. But don't be scared like this. We already taken the differentiation of this. Give us this one, right? So that is the first order differentiation. Then we just take another differentiation with respect to z to the negative 1. So what is it? This one, take differentiation twice, is this one take the first time, which we get this, then take another one. Right? The first differentiation of this is this one. We already done it, right? Then you take another differentiation with respect to z to the negative 1. Again, you can write this in x, but you don't need to in this case. This one, negative 5 plus 2 z to the negative 1. Take differentiation with respect to z to the negative 1. What do we get? 2, right? This coefficient here, right? 2?
Yes.
Yes, right? If you confuse, you write this one in x, then this dx. Now you feel better. So that is 2, right? The same thing, this is negative 1, negative 1. What's different? No difference, just the variable. Right? So that one equals 2. So 2 here, so this part equals 2, then there's 2 here, so that equals 4. 4, and we let z equals half. There's no z here, there's a constant. So no matter what your z is, this is always 4, so that means equals 4.
I still don't understand where you got the negative 2 and the 2 in front of.
This one?
Yeah, B and A, yeah. Is that
Look at your formula. Right? I write here how to find this A, how to find that, let me see. The CM is, if you like, okay, let me write the formula for this. This CR here, okay, I will remove all this. This C here is 1 minus Pi. P is the pole. In our example is half, right? P is the pole. Z to the negative 1 times the highest order. The highest order is M in the formula. But in our example, the highest order is only 3. So that in our, this is why we multiply by to the 3.
Yeah.
Okay, so this is wrong, right? So this is 1, then times 3 here. Right? Here to the 3, right? And this one, then you let z equals the pi. Let z equals the pi. And that one we get equals equal to the first one. That is the formula for the first one. And we did follow this formula. Any question on this? All right, now what's the second one? The second one equal to negative 1 over pi. That is how you get this negative 2 here. Look at this. What is pi? Half, right? 1 over half equals 2, negative 2. So that's why you get negative 2. So that is the coefficient in the formula. And then d z to the negative 1 and xz. This part, there's xz times this, xz times this. And xz times 1 minus pi, z to the negative 1 times m. Like this. And again, let z equals pi. This part gives you the coefficient negative 2 in our example. And take the first order differentiation of this part, which is this part, which is here in our example. And at last, you need to let z equals this pi. Okay? Good? And for this here, and this one equals k minus 1. No, this is the third one, right? The third one is 2 negative pi squared 1 over this. Then I will put this one negative 1, 2 negative pi squared, then d squared, dz squared, and everything still the same. And let z equals pi. So this part same as this, as here. Then take the second order differentiation, but multiply the coefficient here. 1 over 2 negative pi squared. In this example, this gives us 2 here.
Gotcha.
And then let z equals pi.
Gotcha.
Eh?
Thank you.
Okay. So if in the test, if you need to find this formula, either I'll give you or like you have a cheat sheet, you need to write this one, so you can use this. I will. So all we list the formulas are here. Okay, any other questions? Once we find the A, B, C here, A equals this, B equals this here, we just plug into here, then we can check formulas, check the table, then we can find out. That's the trivial, okay? This one is in the formula, okay? In the slide. But you need to know this, right? We discussed the initial value theorem. Still remember that? Initial value theorem. And we said x0 equals the limit z goes to infinity and xz. That is the initial value theorem. And last time when we discussed the initial value theorem, we mentioned the application of this can be used for inverse Laplace Z transform. Today we are going to have another example to show how to do this. Alright, suppose, okay, example by initial value theory. The example is xz equals 1 plus z to the negative 1 plus z to the negative 2 and 1 minus z to the negative 1. First one, let's try the method we discussed today before this initial value theory. How to do this? The first step, we need to determine if this is appropriate. So we need to decide if we need to use long division or not. Is this appropriate?
No.
No, because degree on the top equals 2, degree on the bottom equals 1, so it's not. So we need to use a long division to do this. When we write a long division, we need to use this, we need to in this way, right? So this plus this divided by this one minus plus this. Okay? Then, once we find the long division, then it looks like the next one is good because we have only one root. So must be something, then plus a constant over this one. So that's very simple, right? Does it make sense? Everybody can do this? Okay, now we discuss another method with the initial value theory. We assume this one is a right-sided signal, is causal signal. That means the first non-zero value can only start from 0. We don't have any negative values. We don't have any value for negative time. Okay. So first one is what is x0? X0 is here. Right? So limit z goes to infinity, then xz. Right? For this one, you may want to try to write this in terms of z instead of z to the negative 1, because we always deal with z. Right? So this one, I will rewrite this one. On the top and the bottom, we multiply by z squared first. Right? So this one is z squared minus plus z plus 1 on the top. And on the bottom, the z squared minus z. Very good? Everybody get how we do that? Right? Then what is it? That is Q2, right? The limit, Q1 actually. Right? Limit. What is it? Equals 0. Z goes to infinity. Equals 1. Okay? This one equals 1. Okay, the next one is what is x1? From the initial value theorem, x1 equals xz minus 1 minus this, then times z and take the limit z goes to infinity. Okay, let's see what this is. Goes to infinity. Z minus 1, xz minus 1 is this one. Okay, so I'll write this one plus this. This is xz minus 1 means minus z squared minus 1 here. Right? So that one will be equal to z squared on the bottom minus z on the top. And this z squared is gone. And this z and this z minus minus, so that's plus, so that's 2z, and then plus 1 here. Right? That is this xz minus 1 equals this. Right? Then we times z again, so it's here, then this one equals z. Then times z. equals this. Good? That's easy. All you do by yourself, right? It's just be careful. Something like a bunch of polynomials multiplied together, right? All right, now the limit. What is the limit when z goes to infinity? Right? I will write here z squared plus z over z squared minus z. What is this? What is the limit when for this one when z goes to infinity? Equals 2, right? Equals 2. Right? Then we can do this step by step. X2 equals right? This thing here equals z x z minus 1, or this thing then minus 2, okay? Then times z, then take the limit z goes to infinity. Okay? So this one minus this, okay, so we already have something here, so you can do that. And this limit equals 1. Okay? And you do all this, you find that here all this equals 1. Alright, so now tell me what is xn? Summarize. In general, all xn equals 1 except this next one, this one equals 2. So what is it? How to write this one? We don't like this. You list all these values, right? We need to have like a compact for representation. All values equals 1 except the second one equals 2. How about I use this one equals un? That solves a lot of problems, right? So everyone is 1. Good? But this one needs one more. So we only need to deal with this one. How to add this one to 1? Add 1 to this one. This occurs when time equals 1. So if I put like this, is this good? Yes, right? Huh? This un means all values from 0 to infinity equals 1. But this one means when time is equals 1, we need to add 1 more, which gives us this one. Any questions on this? Okay, next we are going to discuss 2 important properties that can be used for solving difference equation. Right? First one is called right shift theory. of Z transform. I don't think I need to write the derivation or the proof of this, but I only list the conclusion. So if we have Z n, suppose we know Z x n, the Z transform is xz. Suppose we know this. Now, if we delete this by m time, then we want to find the Z transform of this. Right? Or we can just use this here, like this one. So the Z transform of this one is related to xz by, first one we need to have some initial value here, negative m. This is small x, right? That means the value for this for this. Then plus this plus x negative m plus 1, that's the next time, then times z to the negative 1. Okay. And then plus x m plus 2 and z to the negative 2. And so on, until the last term is z to the negative m times xz. Right, let's do an example. Suppose xn give us xz. What is xn minus 1? Here, this small m equals 1. So we have only, this one will be equal to negative 1 here, the initial value, then plus z to the negative 1 and xz. This theorem deals with the initial values also. If in the simplest case, if the signals, the initial value all equal to 0, that means all this equals nothing, 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 then we have only the last term. So that means if the initial value equals to 0, then this one will be only equals this. Oh, that is easy, right? So that means x n minus 2 will give us only z to the negative 2 xz.
Can you repeat what you just said for z?
Which one? I mean, all these initial values equal to 0. So then this one be gone, this one be gone. So we have only the last term. Actually, this one is the property we discussed for Z transform in the previous lectures. This is the end. Remember what is this one? What's this? 1. What is this? Z to the negative 1, right? And this is in the table also. If you look at here, minus 1, this one times this, and this one equals 1. So that's equals. So this is more general. Deal with non-initial values. And this is very important as in the Laplace transform. If we want to solve difference equation with the initial values, we need to use these formulas. This is the right shift. The next one is the left shift, or some call it like advance, or this is called delay or something. This one x n plus m. What is this? This one will be equals of z to the m and x0, then plus no, this one is here. xz, then minus z to the m x0, then minus z to the m minus 1, z to the 1, then minus z to the m minus 2, x2, and minus all the last one is z and x m minus 1. Okay, again, we deal with the initial values here. If all the initial values equal to 0, this is gone, this is gone, this is gone, this is gone. Okay, so we have only this term. Okay? Right, these are left shift theorem and right shift theorem. Right. Next one is solve difference equation. DE, if you take set C323 algorithm or something, sometimes you need to solve. Who's taking that class? Any? No, from computer science. There's some like mathematics, like discrete math or something. You need to solve difference equations. Anyone is taking that class? If you are minor in computer science, you need to take that. So that is an important topic in computer science, let alone in math, right? So it's for solve difference equation. And for our CET design, sometimes we also need to solve difference equation. So we are going to discuss two methods. The first one, iterative method by iterations. Then the next is use Z transform and the inverse Z transform. The difference equation can be written as this form: Yn equals the sum k equals 1 to capital N a k y n minus k, then plus k equal to 0 to capital M and bk x n minus k. So those are the input of the system. Those are the feedbacks, and these are the output of the system. Something like this. We have this system here. You have a x n here. You may this one directly input here, or you may delay by some time, and delay some time, then you back to here, or you may even delay more time here, then you go back to here. So anyway, all this add up together. So usually we do like this. So you have xn, and this is the sum, and you delay by some time, 1 second, and go back to here, and you delay another time, okay, then you go back to here, then maybe we need to multiply by some coefficient. So this one here equals b0, b1 or something, and all these terms add to this, then that is the system. Then the output is here, yn, and this one is delayed by some time, and we also come back to here, then add to this, come back to here, then add to this. So that gives us, this is the discrete system. And we try to solve from this input to get this output. And these are the connections. And the following chapters, we are going to discuss this. But now, we only, once I give you this difference equation, how to solve this one mathematically. We use the iteration method to do this. And actually, we have done this before, right? In the homework, midterm, right? And so what is y0? y0 is n equals 0. So this one will be sigma k equals 1 n a k and y n minus k here, then plus all this k equals 0 capital N b k and x 0 minus k. So that we get this. Okay. So what is y1? Okay, y1 you change this y to 1, then this one change to 1, this one change to 1. Okay. And 2 you change to 2. So you do this recursive as then by iteration. So any time actually just use this form. So that is, we mentioned this before, so I don't discuss the details. You should be able to do this. Next, we are going to use today the new is use z transform and inverse z transform to solve this. Just like in Laplace transform. In Laplace transform, we discuss how to use Laplace transform and inverse Laplace transform to do that. All right, let's do an example. Solve this by z transform. Example here, the yn plus 2 plus 3 yn plus 1 plus 2 yn equals 0, and the initial conditions y0 equal to 0 and y1 equals 1. First one, can you solve this by iteration? So we know y0 equals 0, y1 equals 1. Then you can find y2, right? By iteration. Yes or no? This one equals 0 minus this minus this. Move all these two terms on to the right hand side. Then when n equals 1, when n equals 0, this, let me write this by iteration. Method 1 by iteration. So yn plus 2 will be equal to, move these two terms to the right. So negative 3 yn plus 1 minus 2 yn. Is that good? From here we get this. And there's 0. Before that, 0 minus this. Plus. So what does that mean? y3. What is y3? Y2. Okay? We know y0, we know y1. So the next one we need to find is y2. What is y2? y2 means this n must be equal to 0, right? So that one will be equal to negative 0 minus 3 y, what is here? y1, right? And minus 2 y, what is here? 0. Right? We know this equals this, we know this equals this, so we can calculate this. Does that make sense? So we did this before. Then next one is y3. y3 of 0 minus y3, this one here must be 2, right? And then minus 2, this one must be 1 here. And we know this, right? From here. And we know this, which is given. Then we can calculate y3. Then we do this one by one. That's called by iteration. You need to be able to do this. This is in the first method, right? What we do here is we use the z transform. Right? First one, I will remove all this. You don't need this. Take the z transform on both sides. Step 1, z transform, take zTrans on both sides. YZ, suppose we assume yn give us YZ. Then, so yn plus 2 what is this? This is the left shift theorem. We shift this one to the left by 2. So what is this? This one gives us z squared y0 and minus z squared yz minus z squared y0, then minus z to the y1. So that is y2. Right? What is this? This is given here. What is this? This one is given here. Right? So this one actually equals d squared yz, then minus this one equals 0, right? So just minus d. So this z transform gives us this one. Right? What is the this term? So y n minus 1. What is this? Again, this is left shift theorem, and this one will be equal to z times yz, then minus z y0. That is from the theorem. What is y0? Equal to 0, so that one actually is gone. So this one is only here. Any question on this? Then the last one, yn give us a zn, right? Or give us a yz, so that is here. So what we come out all these terms together. So the first one give us z squared y z minus z, so that is the first term. Then plus, there's a 3 here, so 3. And this yn plus 1 give us this, so that's z yz here. Then this one give us a plus 2 yz here. Then equals the z transform of 0 equals 0. This is just like in the Laplace transform. We just take the z transform on both sides, then we convert the difference equation into a algebraic equation. So this means z equals, you combine terms and shift left. Okay, so this one equals z over z squared plus 3z plus 2. So equals this. Then we need to find the inverse z transform. And this one, we rewrite this one as 1 plus z to the negative 1 plus minus 1 plus 2z to the negative 1. Now, that is the technique we just discussed today, right? Inverse z transform. So we have this one. So from here, what is yn? Then this one. What is this? Un. Right? That's un. What is this? 2 to the n, negative 2, right? So minus negative 2 to the n, un, right? Okay. Un, that means we have not un here, so I just add this together here, then un. Right? So that is the, this one actually is not the un. Un is minus 1, right? So this is plus 1. So actually this one is also exponential. So this is supposed to be a negative 1 n minus negative 2n. Negative 1 to the n, negative 2 to the n. So like this. And this is not un. Un is 1 minus 0. Okay, that is how we solve difference equation with z transform and the inverse z transform.